Welcome. I'm Nan Jokerst. I'm a professor of electrical and computer engineering at Duke University and the executive director of Duke's nanotechnology shared facility called the Shared Materials Instrumentation Facility. Today, I'm going to give you an overview about how to fabricate materials and structures at the nanoscale. The basic components needed for nanofabrication are an extremely clean environment called a clean room, in which there are very few particles. That's where we perform the fabrication work. And number 2, specialized equipment for 3 basic functions: thin film material deposition, patterning, and etching. To illustrate this, let's think about computer chips, which are also called integrated circuits, or ICs. These integrated circuits are made up of structures that include transistors and interconnections between the transistors. These transistors can be very small, with feature sizes that are only tens of nanometers. And this allows us to integrate a large number of transistors into a tiny space to create a powerful computer. To make sure that there are many transistors that work, even a small piece of dust must not land on the chip because it can ruin the circuit. Consider this. In 2009, there were 10 quintillion transistors made in fabrication facilities with clean rooms like the one you will be introduced to in this course. Those 10 quintillion transistors are 250 times the number of grains of rice that were eaten worldwide that year. And for the price to produce a single grain of rice, we can produce 125,000 transistors. These integrated circuits are made with thin materials that we deposit, pattern, and etch, and they're materials such as metals and dielectrics. The machines that perform these nanofabrication steps are the focus of the nanofabrication videos in this course. Let's take a closer look at these materials. Metals are electrically conductive materials such as gold, aluminum, and silver. Dielectrics are materials that are not electrically conductive, such as silicon dioxide and silicon nitride. Both of these types of materials are used in a wide variety of structures and devices, and we often use many layers of different materials in our work. Let's start by looking at some examples of devices and materials that my students have fabricated here at Duke using the tools that we'll show you in this course. First, let's look at lasers. There are many kinds of lasers. For example, in my hand is a common laser pointer. Or if you go to the grocery store, you might have your groceries scanned by laser. Lasers are used in many devices today. DVD players use lasers, and data is transmitted across optical fibers using laser light. The early lasers were all large, the size of a big table. Today, the lasers that we use, especially for portable devices, are very small and are made with the nanofabrication processes that you'll learn about in these videos. These very small lasers are called semiconductor lasers. Here's a tiny semiconductor laser that my students made here at Duke in the facilities you'll learn about. This laser can fit onto the head of a pin easily. The scanning electron microscope picture of this laser shows the metal stripe that pumps electrical current into the laser to produce the output light. In this course, you'll learn about the tools that my students use to deposit, pattern, and etch these metal interconnections. The next example I'd like to show you is called a metamaterial. The metamaterial that I show you here is the first ever reported invisibility cloak, and this was made by the David Smith group at Duke University. This metamaterial is patterned metal on dielectric printed circuit boards that have been bent. You can see that the metal pattern has lines that are about 1 millimeter wide. This metamaterial bends electromagnetic waves around a metal object that we put in the center of the ring. To make metamaterials that operate at different wavelengths, we need to make the size of these metal patterns different. The size of these metal shapes is called the feature size of the pattern, and different nanofabrication tools can make different minimum feature sizes. We can make metamaterials with patterned metal with feature sizes that are much smaller than millimeters to access different wavelengths of light. My students fabricated this metamaterial using a patterning process called photolithography, which you'll learn about in this course. Photolithography can produce feature sizes as small as a couple of microns wide. Let's look at it here under a microscope. You can see the metal patterns on the dielectric material clearly under the microscope. Now, to move even closer to visible light with metamaterials, my students fabricated a metamaterial that has 50 nanometer feature sizes of metal that is only nanometers thick. For this, we need to use a scanning electron microscope to see the metal patterns, as shown here. In this course, we'll show you what tools are used to fabricate these structures, how to image what you've made, and explain how these tools operate. And finally, our students will demonstrate for you how to use the tools. The metal and dielectric layers that we use to fabricate our structures, devices, and integrated circuits are very small and very thin. The thickness of our metals is often about 100 nanometers or less. Compare this thickness to the diameter of a human hair, which is about 100 microns. That's like comparing the height of the Statue of Liberty to the height of an iPhone. Now let's get back to our basic tools that we use for nanofabrication. Thin film deposition of metals and dielectrics, and then patterning and etching of those deposited thin films. There's a variety of equipment that we can use for depositing thin layers of materials. Thin film deposition means that we cover a substrate with another thin material. The substrate is often something that you can hold in your tweezers, like this silicon substrate. For example, we might make transistors in the silicon substrate, and we would need to make electrical connections with metals to those transistors. To make those electrical connections, we could deposit layers of metal onto the silicon substrate, as I show here. And then we would pattern the metal, as on this substrate. Now, in order for any of these techniques to be successful, as I mentioned previously, we need to be in an extremely clean environment in which to work, so that particles of dust, dirt, or even smoke in the air don't become part of our sample. These airborne particles become defects on our samples, and a defect can ruin one or more devices on a substrate. For example, if we're making computer chips on silicon, we make many computer chips on a single silicon substrate, and any of those chips that have a defect, we have to throw away. That means the yield, or the number of good chips that we get from a silicon wafer, is lower. So particulate control is extremely important for nanofabrication. To control airborne particles, we fabricate structures in a clean room. But a clean room alone is not sufficient for our thin films. Most of these nanofabrication techniques are extremely sensitive to any impurities and contaminants, which also decrease yield. These processes are so sensitive, in fact, that the air itself could result in defects that affect the purity of our thin film coatings. So this leads to another requirement for depositing thin layers of high purity materials. We deposit the materials in a vacuum system. A vacuum system is any piece of equipment that has a chamber that provides an environment which is nearly free of all air molecules. Now let's talk about the processes that we use for fabrication in these clean environments. First, let's explore some of the nanofabrication tools that we'll cover in this video series. The thin film deposition that we showed for the metal on the silicon substrate also applies to other materials. There are many ways to deposit thin films of materials onto our substrates, including vacuum evaporation, sputter deposition, and chemical vapor deposition. Depending upon your material and your specific requirements, you may choose any one or a combination of techniques to deposit one or more layers of different materials onto your substrate. You might also pattern each material separately or pattern a whole stack of materials together, and there are many variants on each of these techniques. Another key process in nanofabrication is patterning, which is typically used with thin film deposition. Look at our silicon substrate with metal again. One way to make interconnections to the silicon is to pattern the metal so it can be removed from the areas where we don't want that metal interconnect. Several common patterning techniques are photolithography, electron beam lithography, and nano-imprint lithography. Each of these techniques will be discussed in dedicated videos in this course. All of these techniques are used to create patterns in a variety of materials. Now, after patterning, we often need to etch that pattern into our deposited thin film, which brings us to the third major type of nanofabrication process, which is etching. This is simply the removal of material. Etching is often paired with a patterning technique so that we can transfer a design we've made in a computer into a material by etching the patterned regions of material. Etching is typically grouped into one of two types: chemical wet etching and dry etching. Chemical wet etching is typically performed in a chemical fume hood, as in a chemistry lab, using beakers and flasks containing liquids that might include acids, bases, and solvents. Dry etching uses no liquids at all. Instead, reactive gases are used to etch the materials. Examples of dry etch processes are reactive ion etching and inductively coupled plasma etching. Both wet and dry etching techniques will be discussed in their respective dedicated videos in this course. Now you have an idea of how we fabricate materials and structures, and in the following videos, we will show you in detail how the specialized fabrication equipment in clean rooms works for thin film material deposition, patterning, and etching, and we'll have demonstrations by our students and staff of how to use each piece of equipment.